All right, so I'm continuing assignment 13.4. Last video stopped off by basically saying that, look, a parallel capacitor set has a similar form for total resistance as a series capacitor. Sorry, a series resistance, okay? And vice versa. So the two formulas end up being opposite of each other. Last but not least, we want to know how much energy a capacitor can hold, because unlike resistors, resistors are basically a power supply because current's running through them, it's burning up the current, so there's the amount of energy being used per unit of time based on how much current's going through it. We want to know how much energy a capacitor has. Capacitor, once it's charged, has energy, right? Has ability to do some work. And so how do we figure that out? Well, actually, it's actually fairly straightforward. We know that CV equals Q, agreed? Therefore, by the way, that C equals Q over V, or maybe even more importantly, we've got Q over C equals V. Now, that's an interesting formula there for us to use in just a second. And then we can say, all right, well, wait a second. There's something interesting that happens, though, when you got a capacitor, and that is we know the energy of a system is equal to VQ. Well, that's easy, right? V is the voltage of the capacitor, and Q is the charge it has on it, right? But the problem is this. As the charge goes down, what happens to my capacitance? Sorry, what happens to my voltage? My voltage has to go down as well, because if we draw a formula of voltage versus charge, we would note that this would give us a nice line. And so we're back in the land of, hey, let's do an integral because my voltage goes up as I put more charge on there, so I'm storing more energy. And it's a triangle, so look at that. And we know the bottom of this triangle is Q. Well, Q is equal to CV, right? So if Q is equal to CV, then we could write this bottom as CV, and we could say, aha, the energy stored in a capacitor is equal to 1/2 CV squared. We could also make it, energy stored in a capacitor is equal to, if we recognize what's going on here, we could say, well, CV equals Q, so I could do 1/2 QV, or, in a completely juvenile attempt to make this even more fun, I could do 1/2 Q squared over the capacitance. Again, the last one being CV equals Q, so V equals Q over C, so I can throw that into my equation. So all three of these will give me the energy of a capacitor. Its ability to do work based on how much is currently stored on it and the capacitance of the item. All right, so here's what I want you to do. I want you to try problem number 1. It should not take you long. If you're stumped, have no idea what to do, I will happily do so. Oh, we haven't mentioned what those little F's are. The F's are farads, okay? So it's named after Faraday. Faraday finally got his name on something, and this has to do with capacitors. And so capacitors are measured in farads. That little mu in front of it means microfarads, means times 10 to the negative 6. Most capacitors are in the range of times 10 to the negative 6 because farads, a small capacitor does a whole lot of oomph, at least unit-wise. Okay, so try number 1, and I'll do problem number 1 in just a moment. All right, hopefully you're done pausing. I'm going to set up my screen while you're waiting. File new. Don't save. Okay, so the next one ready to go here. So it says here I have two capacitors. They're connected in parallel. What is the total capacitance? Okay, so we just said parallel is the thing. So capacitance total is equal to capacitance 1 plus capacitance 2 plus ... Ergo, again, we're doing parallel, right? So it's the exact opposite of the way we're used to. I've got 5 microfarads plus another 12 microfarads, which means I have a total of 17 microfarads, and I am done. So that's how you do problem number 1. Go ahead and try problem number 2. I'll join you in just a moment doing problem number 2. Okay, problem number 2, hope you paused. Problem number 2 says draw it, so I'm going to go ahead and draw it. I have two capacitors. They are in parallel, so I'm going to draw them as in parallel. Remember the notation for that is two equally length plates that are equal in length, okay, and then go back down. Okay, so one of these is supposed to be 5 microfarads, and the other is supposed to be 12 microfarads. So there's like a number of ways to do this problem. One of them is to go ahead and just say, well, look, I know what the total capacitance is, so I can find the charge on each capacitor. That's not a problem, but we're going to go, we don't want to know that. What we really want to know is we want to know what is the charge on each of the capacitors. So I'm going to go ahead and go, well, each one gets a 9-volt drop, right? I have to lose 9 volts going from here to here, right? And so therefore it's just CV equals Q. Again, I'm writing the formula the wrong way, but who cares? You guys get to live with that. 12 times 10 to the negative 6 times the voltage, which is 9, gives me 9108. So 1.08 times 10 to the negative 4th coulombs, right? That's the unit for that one. And then my other capacitor is a 5, so 5 times 10 to the negative 6th. I'm attaching a 9-volt battery to it, and so therefore it would be 4.5 times 10 to the negative 5th coulombs of charge. And so that would be the charge on each one of those individually. All right, so that's a piece of cake. So go ahead and try number 3. Pause this video, and we'll do number 3 together in just a moment. Again, it shouldn't take you long, so if you're really stumped, don't stare at it. Just go ahead and forward the video. So here we go. Moving forward, we got 2 capacitors, 5 and 12 microfarads connected in series. What is their total capacitance? Aha! They're in series. So series, we do the opposite of resistance. We do the opposite of resistors. So we're going to use what was the parallel formula for resistors in parallel. We're going to do that for capacitors in series. And so I get 1 over CT equals 1 over, this is going to get a little bit icky because it happens to be micro. So we're going to get 5 times 10 to the negative 6th. It's 5, right? 5 to the negative 6th. Plus 1 over 12 times 10 to the negative 6. This is a physics class, so we're going to get out a calculator. We're not going to do a common denominator because that would be, a minor bit of time-consuming-ish. So if I don't have my calculator again, so I'm going to pause it, be right back. After running it through my calculator, I get the total capacitance would be equal to 3.53 times 10 to the negative 6 coulombs, or sorry, farads. Okay. All right, again, less than the first 2. Why? Because you lose capacitance because you have to power both with the same voltage. Okay, go ahead and try number 4. That's going to cause you to be a little bit trickier. Try number 4 in all earnestness, and then we'll get together in just a moment and talk about how to do number 4. Go ahead and pause it. All right. So I now have a battery attached to it. It's a 9-volt battery. I've got a capacitor. I've got another capacitor. And then I'm bringing it home. So this is a 5 microfarads, and this is a 12 microfarads. So what do I know is true? Well, what do I know is true? This is an interesting situation. I know it's going to store a certain amount of charge based on the total capacitance. We can absolutely do that. We can also say the following, that we know the charge for these is going to be the same, agreed? Since the charge is going to be the same, we can actually do Kirchhoff's law on this if we wanted to too. Because remember, if CV equals Q, then V equals Q over C, agreed? And so I know 0, 1 trip around, is equal to going up 9 volts minus, I'm going to have a Q over C, Q over 5 times 10 to the negative 6th, minus Q over 12 times 10 to the negative 6th. And we would note that we just did this before a second ago with this formula, but that's the bottom line. These Q's have to be the same, so I can solve this pretty straightforward by saying negative 9 equals negative, now I'm going to have to do a little bit of, run it through my calculator grindiness. 1 divided by 5 exponent negative 6, which gives me, why did I do that in calculator? It's a little embarrassing. I get 200,000 Q minus, and then we do the same thing, 1 divided by 12 exponent negative 6, And this one, I get 83,333.3, repeat a bunch of them, Q. I'd add those up, plus 200,000, and I would get, where's my pen? My pen. So I get negative 9 equals negative 283,333 Qs. So take 9 and divide it by that lovely answer, and I'm going to get that my charge on that's being stored is going to be end up being 3.18 times 10 to the negative 5th coulombs. All right. Now, that's one way to do the problem. It's legit, and it actually better.